Based on the definition of paths and circuits, we are going to define two special types of paths and circuits. One is going to be the Euler path and the Euler circuit, and the next one will be Hamilton path and circuit. And an Euler path or an Euler circuit is a simple path or circuit that contains every edge in a graph. That's the definition of an Euler path. And recall that a circuit is a path where the initial vertex and the final vertex are the same, which means you start from a vertex, pass through some other vertices, and end up at the initial vertex you started with. That's we call a circuit. So in the same spirit, an Euler circuit is a circuit which includes every edge in the given graph. So that's the definition of an Euler path or an Euler circuit. A connected multigraph, well, if it is not connected, obviously it's hopeless because you cannot really jump to the other cluster. Let's say if you have something like this, these are connected together in some way, but let's say you have another cluster connected in some way. If you start here, you can never jump to this one. Therefore, you will never find such a path. So they are out of the question. We need the graph to be connected. A connected multigraph with at least two vertices has an Euler circuit if and only if each vertex has even degrees. Okay, so you can find an Euler circuit, something like this, passing through every edge if and only if each vertex has even degrees. Now, this problem has some historical roots, and it's based on what is called the 7 bridges of Königsberg problem. Dates back to 18th century, actually, and this is a town in that times, and there is a river passing through this town, and there are 7 bridges on this river connecting the parts of the town to each other, and people were wondering whether it is possible to pass through every bridge and end up where you started. For instance, you start from here, you pass through this bridge, you go into this island, then you pass through this bridge, you are in this island, and then you pass through this bridge, you are in this island, and you pass through this bridge, and then this bridge here, etc. So is there a way to pass through all the 7 bridges and end up at the same island you started initially? That was the question, and Euler had an answer to that, and he actually proved that it's not possible because you see, well, this is the real geographical map of this town at that time, and this is in the middle is a sort of a simplification, and on the right hand side you see the graph representation of this structure, and clearly you see we have, for instance, this vertex with a degree of 5, this one with a degree of 3, and the others also degrees of 3. Now, to be able to do this, start from any vertex to end up at the same vertex, you should go, so you leave that vertex and then come back. You can repeat this procedure, but you leave it and you come back. You leave it and you come back. That means it has to have an even number of vertices. And this property turns out to be essential for the entire graph. So Euler has shown that a connected multigraph with at least 2 vertices is possible to have an Euler circuit if and only if each vertex has even degrees. So in this structure that is not satisfied, therefore the answer to the 7 bridges of Königsberg problem is no. Now, when it comes to Euler path, a connected multigraph has an Euler path, but not an Euler circuit, if and only if it has exactly 2 vertices of odd degree. And this is simple to understand because if you have an Euler circuit where your graph has vertices with even degrees, if you remove just one of those edges, then two of your vertices are going to have odd degrees, but then that will define you an Euler circuit, sorry, an Euler pad instead of a circuit, because what you are doing is simply removing one edge here. So you are breaking the circuit and you are you obtain a pad from the circuit. Now, finding Euler circles is not that difficult, and we have algorithms that are linear in the number of edges, and clearly it's not really easy to do it in a better way, because, well, you need to pass through every edge, so you need to process every edge. So it's natural that the algorithms are as good as this. And some applications of Euler circuits and Euler pads are in transportation networks, in DNA sequencing, and in circuit design, and also in logistics, where you design pads for instance, your lorries that carry your either waste material or your products or your raw materials, etc. But it has applications in a variety of subjects.